gave back the homework papers and the quizzes to all of you guys. Everything is posted online at this point. I put up the solutions to the homework that you just did for yesterday. They're already up. You're probably not going to get those papers back, though, until possibly Monday before class, if you come by. I'm not sure when my grader will be able to get them done. So be sure to look at the solutions that I posted if you need to review anything or if you weren't sure about anything. So yeah, this is just a review session for the third midterm. And the sections that the exam is going to cover, I have put them in kind of into three groups here. There's the sections 5.6 through 5.8. That is all about eigenvalues, eigenvectors, diagonalizing a matrix, trying to decide if a matrix is defective or not defective. When it's non-defective, which is another word for diagonalizable, you can find a matrix capital S and capital D, and S is invertible, and so S inverse times A times S is equal to D. Right? And the usefulness of that is that when you work with a diagonal matrix, calculations are very simple to do. And so if you can convert from the matrix capital A that I gave you through this S inverse AS calculation to a nice diagonal matrix D, then it's easy to solve problems. We did an example of that with the, if you remember from class, students switching between two sections, two professors are teaching. That's an application of diagonalization. There's one in the review packet as well about ants crawling between two different rooms of a house, which was actually happening to me at the time when I wrote the question like several years ago. So I was like, okay, this is quite timely. So you might want to take a look at that. And so that's the main gist of this first part. And I would suggest that you just view this as 1/3 of the course material for this midterm. Then we moved into chapter 6 and we started on basically higher order differential equations. Okay, so we had, first of all, we recognized that a linear differential equation, right, can just be viewed as, well, there's some operator, L is what we called it, and what we were looking for was, at least in the first couple sections, we were dealing with homogeneous linear differential equations. So it was really L of y equals 0, which means we were looking for the kernel of L. And the kernel is a subspace, so it has a basis and a dimension, and we can span it with a linear combination of vectors. Okay? Then in sections 6.3 and 6.7, we addressed non-homogeneous linear differential equations. And there were sort of two types of those, or two methods that we learned for handling a non-homogeneous linear differential equation, which was the annihilator method and the variation of parameters method. And that part of the quiz that I gave back actually was quite good. Most people did pretty well on that part. It was really the diagonalization thing that bothered everybody. So anyway, so maybe about 1/3. I'm just giving you a rough estimate here. It might be a little less than that. It's hard to say for sure. But an approximation. Oh, there's also the Wronskian. Right? The Wronskian for a set of scalar functions is used to test for linear independence. Okay? So all of that is kind of in the middle section here. And then the last section, this is the section you got to be a little bit careful about because it came kind of towards the end, sort of post-Thanksgiving in a way, so people were still trying to get their bearings again after the break. But about 1/3 of the exam may be focused on these sections. This has to do with vector differential equations. So in other words, you have a system of differential equations, and that means you have a number of unknown functions, and you're trying to solve for each of those unknown functions, which is like a vector. So we also had a Wronskian here that also tested for linear independence of vector functions. It's not the same Wronskian as what we were using over here. Okay, so this is a different Wronskian. And what else did we have there? We just learned how to write down the solutions to the linear systems. Basically, you use the eigenvalues and eigenvectors of the matrix to build the solutions. and find the general solution. We do sometimes have an issue if the eigenvalues are complex numbers. So I think I'm probably going to make sure we practice that again today, because the situation where the lambdas and the v's are complex, I really only had time for one example of that in class, so I'd like to do another example or two of that with you guys today. Okay? So that's just a brief overview of what this section is going to be about. It's, again, not that much material, and there are connections. You know, the eigenvalue, eigenvector stuff here connects up again over here, right? So you sort of see it coming together. So it's not really that overwhelming. But you should definitely try the sample test. Try the problems in the review packet. Keep in mind that I did not cover section 7.5. So there are a few places where I tried to find all the places I could where there were questions from 7.5, so I could alert you to not worry about those sections, because obviously I'm not going to ask you about them on the test. I will probably do my usual thing on Monday, which is I will start class with sort of just a brief lecture on something that won't be distracting for the midterm, but it'll be very short. And then I'll let you have, as usual, the rest of the class period, and then some, if you need it, to work on the questions for the test. Okay, so that's kind of what you should expect. Pretty much the same format that you've been seeing on my other midterms. Mostly a computational exam, right? Mostly calculations, procedures, going through the motions of problems that are very much like the homework. But I'm not beyond maybe asking a couple of questions where you have to know a little bit of just the general theory. But those tend to work well in the eigenvalue, eigenvector section especially. So, for example, if lambda is an eigenvalue of A and mu is an eigenvalue of B, then if I take A plus B, right, then lambda plus mu, right, could be an eigenvector of A plus B, assuming it's the same. I'm sorry, an eigenvalue of A plus B, assuming it's the same eigenvector for both. So stuff like that. You've actually done a few problems on that. So if you're looking for like some theoretical problems to go over, I would suggest that you take a look at problems, let's see, 36 through 38 on page 399. So that's over in this first section, page 399. You've already done these in the homework, but it was before Thanksgiving, and so that'll give you a feeling for the kind of theoretical problems that I might ask you about. Okay? Any questions about what's going to be happening on Monday? It'll be the same format as my other exams have been. Same kinds of, probably some multi-part problems. Buddy, could you not sit in this row? Maybe sit over on the sides, because I'm trying to do a video of the lecture here. Sorry. That's okay. Okay, so we're all good on all that? The rest of what I want to do, for however long it takes, is go through some practice problems. Now, I posted the questions from the review session that I wanted to do here. One of them, which I think is problem 4, involves section 7.5. So I'm not going to go over that one. But I thought instead of that, so that was problem 4 on this review session questions sheet. Instead of that, I think I'm going to warm up though with, I'm going to add a couple of other problems that have to do with diagonalization, just based on what I saw on the quiz. I think maybe it'd be good to practice a little more on that. Okay, so let's go ahead and take a stab at some practice. Okay, so this is practice problems. Maybe what I'll do is I'll call this problem number 0, so it doesn't get confused with the ones that are on the sheet. Okay, so here's what it's going to say. Determine bases for each eigenspace of the matrix capital A is equal to 9, 5, -5, 0, -1, 0, and 10, 5, -6. Okay, so let's try and find bases for each eigenspace. Okay. Does everybody remember what an eigenspace is, what that word means? Yeah, it's really a null space, right? An eigenspace, our notation for that was usually E sub lambda, right? And what that stood for, the eigenspace, this is the eigenspace corresponding to whatever lambda is, and so this is just the null space of A minus lambda I. Okay? The null space of A minus lambda I. Okay, so to find the eigenspaces, I obviously have to know the eigenvalues, right? That's always the first step. Can anybody remind me, how do I find the eigenvalues? Right, I subtract lambda from the diagonal and I get a new matrix that I do what to? Determinant, exactly. So we're going to take the determinant of 9 minus lambda, 5, negative 5, 0, negative 1 minus lambda, 0, and 10, 5, and negative 6 minus lambda. Okay, this is our matrix. And by the way, this is the part of the quiz that went the worst of everything. It was just getting these lambdas in the first place. And you have to be able to do it, because otherwise you can't do the rest of the problem. So, all right, so this is what we need to do. Now, you could use the arrow method. It's a 3 by 3 matrix. We know the arrow method, right? That'll give you an expression, but will it be in a friendly form that we can find the lambdas from? Not at all, right? Because it won't be factored into pieces, yeah? It won't be factored into separate parts that show me the roots. So the arrow method is not a good idea. What other methods do we have? Pardon?
Expand the row.
Okay, cofactor expansion is the word I'm looking for. But we have to always be careful that we choose the row or column wisely. A number of people on the quiz were not choosing the proper or the best row. It's not that there's a wrong row or a right row or a wrong column or a right column. They're all going to be correct. But the issue is just computationally, it's so much more difficult if you don't choose a row that has, or a row or a column that has nice numbers in it. So what row or column should I use here? I should use the middle row, correct? Because the reason is I have zeros here and here, right? Now you're just depending on whoever's writing the question to make sure that you've got a matrix that this is doable for, okay? I mean, if I give you a matrix that has, 9 non-zero numbers, then there's not much you can do about it, right? You just have to deal with what I give you, but trusting that I'm going to be fair about it, you're going to see something like this just like you did on the quiz, okay? So I'm going to expand the middle row, and remember that we have a pattern. We have to go all the way across this row, but the first and third entries will be 0. So it's really only the middle entry, and remember we have this positive, negative, positive, alternating signs behavior going on. So if I take the 2-2 entry, that's the only one I care about, that has to be taken with no sign change, right? When I write plus, it means no sign change. So I leave it exactly as I saw it, which was negative 1 minus lambda. And then I have to cross off that row and column and take the 2 by 2 determinant. And guys, parentheses are so important here. You have to be not afraid to draw brackets, parentheses, and everything else that will keep it all separated. So now I'm doing the 2 by 2 determinant of the 4 corners of this matrix. So I'll get 9 minus lambda times negative 6 minus lambda, and then plus 50. It's really minus negative 50, but that's plus 50. Okay? So this is what I come up with. Do I want to multiply that out? Not the whole thing. If I multiply the whole thing out, I'll get lambda cubed, I'll get some cubic equation, I won't know how to factor it, right? So what I can do is I can multiply out the part that's in the brackets. You see why it's so good to have the brackets there so you can keep track of that. The negative 1 minus lambda out in front is already good to go. We don't need to do anything to that. Okay, so the part in brackets, I've got a lambda squared, and then, what is this, minus 9 lambda and plus 6 lambda? That would be minus, pardon?
Yes.
Minus 3 lambda, when I simplify that. And then I have minus 54 and plus 50. So that comes out to negative 4. So far so good? Okay, and so now this hopefully factors nicely, but if it doesn't, since it's only a quadratic, you will at least have the recourse to use the quadratic formula to find the lambdas. Okay, but in this case, I think we're going to be just fine to factor it as lambda minus 4 times lambda plus 1. Okay. Now the other thing that okay, so we have 3 factors here, right? 3 different things. And what we want to do is, of course, set this equal to 0, right? Set this equal to 0. So the issue now is that a lot of people have been getting the signs wrong on this. Remember, for example, if you have a factor of lambda minus 4, the root that corresponds to that is not minus 4. It's actually positive 4. Just always ask yourself, what do I have to plug in to get 0? So if I put in lambda equals 4, then 4 minus 4 will be 0. So lambda equals 4 is one of my roots. And what are my other roots? Negative 1 twice, right? So I have 4 and negative 1 and negative 1. By the way, will you guys let me give you a little trick? I'm not going to explain it right here, but I'll get you all to take Math 307 and then you'll find out why this is true. It turns out that if you add up the lambdas, this is just a quick little trick. You add up the lambdas, it has to be the same as when you add up the main diagonal of the matrix. It's kind of a crazy deal, but it allows you to kind of check your answers. So if I add up the main diagonal, 9 plus negative 1 plus negative 6, that adds up to 2. So my lambdas over here have to add up to 2. See that? So that's kind of handy. You like that? That's kind of handy to know. Okay, so when you add up, let me just make that as a note. I should have done it in the lecture, but I just never got around to it. The sum of the eigenvalues of capital A, when you add the eigenvalues, it is equal to the trace of A. The trace of A, have I defined that before? The trace of A is simply A11 plus A22 plus ... plus ANN. If I mentioned it, I only mentioned it briefly in passing, way back when I was first describing properties of matrices. Okay, so that's kind of a handy thing to know. There's another little trick, since you guys liked that one so well. Do you want another one?
Yes.
If you multiply the lambdas, so here's another note. Tell all your friends to watch this video if they're not coming to the review, because otherwise they're not going to know this little trick. If you take the product of the eigenvalues of A, now this one's a little harder to check, but it is equal to the determinant of A. It's actually equal to the determinant of A. So the reason I say it's harder to check is obviously I have to do some work to find the determinant of this matrix. But if we've done things correctly, the product of these lambdas, if I multiply them, 4 times negative 1 times negative 1 is 4. So I can tell you that the determinant of this matrix has to be 4. Okay, for whatever that's worth. That's kind of handy to know. I mean, one way to understand why that's true is that how do you find the lambdas? Well, you take the determinant of A minus lambda I. This is what we call the characteristic polynomial. You remember that? Characteristic polynomial for the matrix capital A. And this characteristic polynomial, what you ultimately try to do with it is factor it, right? You end up trying to factor this thing. And when you factor it, you know, let's see, you're subtracting lambdas off the diagonal. So you're going to get various, when you factor this characteristic polynomial, you're going to get a bunch of linear factors like this, right? Basically, it's a polynomial of degree n. As you see here, this is a polynomial of degree 3. So it factors kind of in this format, and then the idea is that the roots are just sitting right here, right? So you can see that here. Here's -1 is one of my roots. Now this one's flipped around, right? So this is really, well, 4 minus lambda, right? So it's equivalent to 4 minus lambda. So my next root is 4, and this one is like -1 minus lambda, which means I get -1 for a root there. Okay, kind of make sense? Well, if you just simply plug in lambda equals 0 here on both sides, if you plug in lambda equals 0 on both sides, on the left side you get determinative A, and on the right side you're getting all of your roots. That's what the R1 through Rn are. You're getting all of your values of R that make the right-hand side come out to 0. So the determinant of the matrix is the product of the lambdas. Okay, so these are just a couple of important facts to know. They can be handy. They can be handy. Okay. So for example, if a matrix is invertible, then the determinant's not 0. And since that's equal to the product of all the e-values, none of the e-values can be 0. So if you have an invertible matrix, 0 will never be an eigenvalue. But if you have a non-invertible matrix, like the one on the quiz, then 0 must be an eigenvalue. So that's just another corollary or result coming out of this second.
Can you write that as a note, please?
Pardon me?
Can you write that as a note?
You also want that as a note. You got it. Put it up here. No, I agree.
It's important.
It is important, and we'll memorialize it on YouTube. For the whole world to see. Okay. So this is almost like an extension of the invertible matrix theorem. But what we're saying right now, and I'm getting off topic of actually solving this problem, but that's all right. I'll get back to it in a second. So this is like a note. Yet another note is that A is invertible. And that just means, i.e., the determinant of A is not 0 if and only if all of the eigenvalues of A are not 0. Okay? So an invertible matrix has all of its eigenvalues being non-zero. So, for example, this is an invertible matrix. Just want one quick illustration of it. Excuse me. Okay, so we've got the eigenvalues. Can somebody tell me, we'll go back to this problem now, how many eigenspaces do we have?
3. What's that?
Pardon?
What's that? Sorry, bases or eigenspaces?
How many different eigenspaces are there? Just 2, right? There's an eigenspace for each of the lambdas that we have. So we have 2 different lambdas. So there's only 2 eigenspaces.
3 bases.
Say again?
One should have a base of 2.
Well, actually, so let me ask you this question. Do we know if this matrix is defective or not defective yet? No. Why not? Because we have a repeated eigenvalue, it's sort of up in the air. I saw a lot of people on the quiz, they got a repeated eigenvalue and they circled not diagonalizable. Right? You can't do that, right? You have to go further and actually compute the eigenspaces first to see whether these eigenvalues pull their weight. This one has a weight of 1 and this one has a weight of 2. So which eigenvalue would make sense to deal with first? Negative 1, exactly. So let's try it. Let's do lambda equals negative 1. Okay. Then we're going to calculate the null space of A minus lambda I. That would be A plus I in this case. So that's just the null space of the matrix that I get by adding 3 to the main diagonal. So I have 10, 5, I'm sorry, by adding 1 to the main diagonal. 10, 5, negative 5, 0, 0, 0, and 10, 5, negative 5. The matrix that you come up with here, remember folks, it has to be not invertible. And pretty much just obvious that it isn't because you have a row of zeros there, right? And the first and third row are the same, so I can wipe one of those off. You guys can be real slick and quick with your EROs, but just be careful to not make any mistakes by going too fast. Okay, so I don't need you to show all that work. This is basically going to be your pivot, okay? And you're going to have 2 free variables, which I guess I'll just call them y and z, which are going to be r and t. Everybody seeing that? So then when I solve for x, I have to use the first equation. So I guess the first equation, if I write it out, it says 10x plus 5y minus 5z is equal to 0. But if I solve that for x, I'm going to get 1/2 of z, which is t, minus 1/2 of r. Okay? By the way, can you tell at this point whether our matrix is diagonalizable or not?
Yes, yeah.
It's looking pretty good, isn't it? Because I've got 2 free variables, so I know that the dimension of this eigenspace is going to be 2, which matches the weight of the eigenvalue. We called it the multiplicity, if you remember. The multiplicity of negative 1 is 2, and we're getting 2 free variables here. So it's just the usual thing. If I want to get a basis, that's what I've asked for, determine a basis. The basis here, what you're going to do, and I'm going to just kind of jump to the answer because I think you guys have done enough of these that you know what's going on. We're just busting out variables here, right? It's always a good idea, by the way, when you're doing this, always list them in the proper order, x, y, z, so you don't have to make any changes to it mentally later. So put it in the order it needs to be in, and then you can just bust things out vertically. So if I bust out the t, I'm going to get 1/2 and 0 and 1. And if I bust out the r, I'm going to get negative 1/2 and 1 and 0, like that. Okay, so that would be the basis for that eigenspace. On the other hand, let's do the other eigenvalue, which was 4. So when lambda is equal to 4, we're going to subtract 4 from the main diagonal and take the null space of it. So it's the null space of, let's see what we get. We're going to take 4 away from the main diagonal. So 5, 5, negative 5. And then 0, negative 5, 0. And then 10, 5, negative 10, if I did it right. Okay, now guys, that may look like, oh, it's going to be a lot of work right now. I want to remind you it's not that bad. Because look at the middle row. Remember, you have 3 variables here, x, y, and z. Based on the middle row, what can you tell me about y? It's 0, right? Because you have negative 5y equals 0. That's what the second line tells you. Right? Stop me if I'm saying anything bizarre. Because it's okay. Don't feel like there's no silly questions here. Okay? Even though it's something we did a while ago, sometimes people just need a refresher because there's been so much material that's gone by. That middle row just reads negative 5y equals 0. There's no x and there's no z because of these zeros. Okay, it's really an equation. So y is 0. We can put that in immediately. Now the minute that y is 0, then when I start thinking about, for example, the top equation, it looks like there's going to be 3 terms to it, but do I need to worry about all 3 terms? No, because the middle term is going to be multiplied by 0. So it's really just the 5 and the negative 5, right, that I'm going to